All right, good afternoon, everybody, and welcome back to the Georgia Tech Manufacturing Institute's Fall 2023 Lunch and Learn Lecture Series. My name is Dr. Billy D. Brown, and I'm Senior Research Faculty, Education and Workforce Development Director for GTMI. I'm excited to continue hosting this series and want you guys to spread the word, to your network so we can continue to grow our audience and provide value to the GTMI community. Before I introduce today's speaker, I'm going to first introduce GTMI and give some instructions for the audience. GTMI is one of 11 Georgia Tech interdisciplinary research institutes, including GTRI, that uniquely focuses on manufacturing, research, development, and deployment. We help tackle the grand challenges of advanced manufacturing, today's manufacturers, and assist partners in moving innovations from the lab to the market. GTMI has a wide variety of facilities and equipment here on main campus for basic research, as well as on 14th Street for more applied research in our advanced manufacturing pilot facility. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI's AMPF, Advanced Manufacturing Pilot Facility, is the headquarters for a groundbreaking initiative called Georgia AI Manufacturing Technology Corridor, or Georgia AIM. This was funded recently by the Build Back Better EDA grant worth up to $80 million. Georgia AIM is expected to profoundly impact Georgia and the nation's economy through equitable development and deployment of talent and innovation in artificial intelligence for all manufacturing sectors. The AMPF currently has state-of-the-art equipment in metal additive and hybrid manufacturing, and is currently expanding and transforming into a demo facility for automated smart factories that incorporates IoT, AI, digital and robotic manufacturing technology. GTMI hosts a Lunch and Learn lecture series each semester. These sessions are excellent opportunities for Georgia Tech faculty, undergraduate, graduate, and researchers, as well as the global manufacturing community to share advanced manufacturing knowledge. Today is our second lecture for the fall semester. We're both in person and streaming online via Zoom. We want these sessions to be interactive, so please, if you have questions, feel free to. We want you guys to chime in and ask your questions. If you're online, please put your questions in the chat, and we'll answer them promptly at the end of the presentation. Today, I'm pleased to introduce Dr. Juan-Pablo Correa-Baena, who will discuss challenges and opportunities in perovskite homelessness. Dr. Juan-Pablo Correa-Baena is an assistant professor and the Gazeta Junior Faculty Chair in the School of Material Science and Engineering at Georgia Tech. His group focuses on understanding the relationship between chemistry, crystallographic structure, and the properties of emerging semiconductor materials. Juan-Pablo is developing deposition techniques, such as atomic layer deposition, thermal evaporation for hybrid organic and inorganic materials with atomic and nanoscale controls. This group is also developing advanced characterization methods, including synchrotron-based X-ray scattering and fluorescence, to answer fundamental questions about metastable hybrid materials. This research program has attracted funding from the Department of Energy, the Department of Defense, the National Science Foundation, industry partners, and foundation, among others. His work has been cited over 32,000 times, H-index of 62, making him a top cited researcher as recognized by the Web of Science Group, a highly cited researcher since 2019, and Nature Index leading early career researcher in material science. In the following presentation, Juan-Pablo will discuss the role of crystal surface structural defects on optoelectronic properties of lead halide perovskites through synchrotron-based techniques. The importance of interfaces and their contribution to detrimental recombination will also be discussed. Finally, a discussion on the current state-of-the-art of performance and stability will be presented. Pablo.
Thank you very much. Thank you very much for the kind introduction. Hi, everybody. So I decided also to zoom out a little bit and not just focus on the research that my group is doing, as Bill just described from my abstract, but also to tell you a little bit more about what kind of things we're doing in the industry and how we can at Tech capitalize on some of the new developments around photovoltaics in Georgia. So I guess the first thing that I wanted to do is to let you know that I'm also now the point of contact for photovoltaic research at Georgia Tech. So I'm one of the initiative leads from IMAT, Institute for Materials, and the Strategic Energy Institute. So basically what it means is that research areas related to photovoltaics, if you're interested in learning more about that, if you have a partner that is interested in that, or if there's anything related to photovoltaics that can catalyze more activities around photovoltaics, reach out to me because I'll be very happy to help connect faculty, students, and industry. So that's kind of something that I'm already doing. I'm talking to Q-Cells to see how Q-Cells can benefit from the expertise all around the tech, and not just the material science, but anything from data processing to artificial intelligence, right? And so that's something that I'm missing there and under my name there, but I'm called the initiative lead for solar. So that's something that is additional there. Okay, so if we are gonna zoom out, what we want to look at is how much energy consumption we currently have and what we can forecast for the next 10 or 20 years. And currently we're consuming, and this is maybe a little bit of an outdated number, maybe we're in the 20 terawatt per year energy consumption. And so this is what we're currently doing. What's going to happen in the next 20 to 30 years is that we're going to double that. And so this obviously presents a challenge. Okay, because most of the energy production comes from fossil fuels right now, which impact the environment. And if we keep consuming more electricity, there's going to be a certain point where that source is going to be depleted. So we really have to look at alternatives, and renewables have been pitched for many decades now, and we're finally starting to see them kind of being part of the equation, right? So now we have large amounts of solar and wind being deployed in a way that actually makes economic sense. So target of 30 terawatts. In terms of capacity that we can estimate from several studies, we can get about 2 to 4 terawatts per year. Maybe that goes an order of magnitude higher if we were to fill a lot of dead space with wind, but realistically under 10 terawatts per year. Hydroelectric also around 4 to 5, so less than 10 terawatt per year. Geothermal about 10 terawatt per year, and then solar, if we were to fill our whole earth with solar panels, which we're not going to do, would be several orders of magnitude higher. So 36,000 terawatts per year. Obviously, we're not going to fill up our whole land with solar panels. So, but even if we do that for thousands or 10,000s of the lands that we have, we will be able to power or to fulfill the necessities of power. And you can imagine that we have a lot of rooftops that are not being used, right? So warehouses everywhere, especially in the Southeast. There's a lot of warehouses, and they're not being utilized with solar panels. One, you have the additional costs of pulling down that facility, which would be removed if you have a solar panel, but then you also create electricity, right? So we're able to fill a bunch of the dead spaces that we have with solar panels. We really would have an advantage, and that is actually happening right now. So here's a nice graph of solar panel costs, which is this line here, and this should be shaded red, but you can see the cost of what it was in the 70s. Don't worry so much about the cost, but very high costs. And over time, they started decreasing, right? And it decreased because of many reasons, because of economies of scale, because technology advances, because people started to care about it, because governments invested money in subsidies that then that translated into lowering costs. And you can see here the deployments or installations all the way to 2015. So that of course has skyrocketed. Even you can see that trend kind of continuing and seems like an exponential curve for now. And what you can see is that this really was correlated, right? So this the amount of the cost of a solar panel is directly correlated to how much we're deploying, and that makes sense. The cost is lower. Now we're reaching costs that are comparable to grid. The grid, what we're paying out of the grid, which is mainly fossil fuel. And once you reach that grid, what we call grid parity, where basically we have a cost of energy coming from solar being the same as the cost from coal, other fossil fuels, then people start thinking about it, right? And now we're actually below the cost of coal in terms of the cost of energy from a solar panel. And so that now becomes an incentive for industry to come in and say, okay, we're gonna make money out of this, even without subsidies. This is the energy production of different sources of energy. So here we have solar, other renewables, we have nuclear and fossil fuels. So still a majority of it by 2022 were coming from majority of resources were coming from fossil fuels and some other renewables that includes biofuels, thermal, and hydropower. Nuclear is a small and steady and maybe even decreasing source of energy because of a lot of the plants in Europe that have been kind of phased out. And so, of course, what I'm interested in telling you today is about photovoltaics, what is going on here at Georgia Tech, and also what is happening in my group, and how do I think as a Georgia Tech can contribute overall to this picture. So let's start with silicon. The group of Ajit Rohatgi here in the first row, Ajit and team have been pioneering a lot of the work here at Georgia Tech with USEP, the University of Center of Excellence in Photovoltaics Research and Education, was founded in '92, but even before, the group of Rohatgi was making very important discoveries and inventions around silicon solar cells. So Georgia Tech has had a very strong presence in the photovoltaic research from very, very early on. Here are some pictures from Suniva, which was a spin-off from the group of Ajit Rohatgi. This slides here, courtesy of Professor Rohatgi here. Showing that a lot of the technologies that were developed here at Georgia Tech were translated into industry. Of course, we know what happens in early 2010s, where a lot of the companies in the US couldn't make it economically feasible to produce silicon wafers, ingots, etc. On site, mainly because of the competition from lower costs from Asia. And that was driven mainly by subsidies from the government, subsidies and cheap loans, right? And so, for the past 10 years, we've been seeing this kind of stagnation of technology in the US around clean tech. And that's something that has been worrying politicians. It has been worrying all of us because we're producing a lot of the technology in our labs, but we're not actually translating that into industry. But last year, the IRA, Inflation Reduction Act, was passed, and that has spurred a lot of incentive and activity around not only photovoltaics but batteries and other clean tech here to be made here locally, right? And so Q-Cells, which is a company that is based here in Georgia, has been here for many years. I think under 10 years, but a considerable amount of time assembling solar panels in Dalton. So they have this beautiful facility that I visited actually with Tom Cortes last year with Matt McDowell and others, where they assemble their panels. But you can see here you have these little cells, right? So those are wafers, and those wafers are kind of one next to the other. And those wafers are actually not made here. And so when we went to visit, that was my first question: where are you getting your wafers? Because we don't make those in the US. At least not in large scale for a plant that is producing such large amounts, such large volume of solar panels. And they said, okay, well, yeah, we buy them from a provider in Asia, and of course they're not allowed to tell any details, but that was to me the key that okay, we're not producing the core technology in the US, which is the actual cell, right? So a lot of most of the work, if not all of the work, is being done by the cell. The rest is packaging. So what we were doing in Dalton, right here, is basically packaging. Right? So bringing all these things, putting them together, keeping them off. And that was not enough. And the Inflation Reduction Act, what has been doing is incentivizing companies to bring the whole assembly, the whole supply chain back to the US. And so point number 2 here, that's Cartersville there. Just, very close to Dalton. And, here we have Atlanta, south, west of that, east of that. And we have now an investment from Q-Cells of 2.3 billion in the state, where they're trying to bring ingot manufacturing, the wafer processing to site, and have this kind of vertically integrated supply chain. So the first steps happen here in Cartersville. Then we make the wafers, or they make the wafers, and then they bring them to Dalton for assembly. So this was a huge thing because for the first time in many years, we're bringing kind of the whole supply chain under one roof that we consider Georgia. Okay, so that's kind of big picture of what's going on in terms of research, in terms of developments of industry and how here at Georgia Tech we can contribute. And so here is an idea that Professor Rohatgi and I have been working on for a while, which is to incorporate a silicon solar cell, which is the silicon solar cell made in Professor Rohatgi's labs, and a perovskite solar cell, which is something that is made in my labs. And can we sandwich them together to increase light absorption, to increase the voltage of the device, while not losing on photons that will give us current. So basically current matching through engineering of these band gaps of these materials. And in this case, we have a silicon solar cell that is opaque. So it's going to be very difficult to have light coming from the bottom because it's opaque, light is not going to go through. But in our case, perovskite solar cells can produce high efficiency devices with very thin layers and be semi-transparent. And not only that, but we can also change their band gap. We can make the band gap be 1.5 or 2 or 3 electron volts. And that gives us a lot of flexibility with engineering of this top cell. Why it matters is because the silicon solar cell has a 1.1 electron volt band gap that is fixed, and it is very hard to change. Actually, I would say nobody has even tried to change the band gap because it's just it's not possible through by having just silicon material. Would have to go into maybe some alloys or some compositional changes. So silicon solar cells make 26% devices. We put a perovskite solar cell that we can tune the band gap so that we let some light through and basically be able to have an additional voltage, right? So if this cell here has a 1 volt and this cell has a 1.1 volt, after a lot of recombination happens, maybe we have a 1.8 volt device. And that almost doubles the amount of voltage that you can have in the device, while minimizing how much loss we have in terms of the photons that are coming from the top. And so the key here is that we have tunability of the band gap of this device, of this material, and also that we can make them semi-transparent. So light goes through and interacts with this bottom cell as well. So that, I won't talk too much about the silicon part because I'm not an expert in that. But I will tell you a little bit about what we're trying to do in terms of perovskite solar cell development here at Georgia Tech and some of the projects that we're doing. So to start, I always like to show this graph of perovskite solar cells that have been in the market in let's say in the research field for only about 10 years. You can see that they're started in the 2010 and 2011, and these other technologies already existed. So gallium arsenide, crystalline silicon, cadmium telluride, 6, all these technologies have been in the market, either in the market or adjacent to the market or trying to get into the market. Actually, all of these you can buy in one way or another commercially. And you can see how long it took for these materials to kind of rise through inefficiencies, right? So 20% efficiency is kind of the mark that we always try to look for in a solar cell. If we're able to get to 20%, we know that there's a lot of potential for this technology. And so you can see crystalline silicon decades. Gallium arsenide actually goes even further back than the 70s. Cadmium telluride and 6 also took decades for us to get to that 20% efficiency. And you can see what happened here with perovskites. In just 10 years or so, researchers like me in the lab were able to get to now 26%. We're right around the same efficiency as a crystalline silicon solar cell, 26.5, I think, percent is the crystalline silicon, whereas perovskites are at 26.1. So really, really fascinating growth in efficiencies. And not only that, but also looking at the techno-economic analysis of some of these materials, we can see that we can have very, very low costs for that specific perovskite solar cell if we are able to get efficiencies in the 25 or 20 to 30%, basically this window here, and lifetimes of 20 to 30 years, right? And actually this here is the biggest challenge. How can we make the solar cells last for 20 to 30 years like silicon? Because if we had that, I wouldn't be talking to you right now. I would have a startup and I would be making a lot of money. But really it is if we're able to solve the lifetime problem, we would be able to make this technology basically replace any sort of current state of the art. And so let me tell you more about this perovskite solar cell as we dig deeper, and the kind of the reason why it's so cheap to make, so easy to make, and why we've made so much progress in such little time. So we have a glass substrate, which is this dark gray box here. We have a conductive contact, which can be fluorine doped tin oxide or ITO or FTO or ITO, which is indium tin oxide. We have a low cost material that we put here that's going to be an electroselective contact. It's going to be an oxide like titanium dioxide, very cheap to make at very low temperatures. Perovskites, the perovskite is going to be a 500 nanometer layer that is going to be also made at low temperatures of about 100 degrees Celsius, and the whole contact, which is also made at sub 100 nanometer temperatures. And then we top it up with an electrode. So light actually comes from the bottom here, if it's the glass, or if we have a semi-transparent electrode like ITO, then we have light coming from this side. We're thinking of a tandem, for example. Here's a cross-sectional SEM with all the different layers, the perovskite kind of being sandwiched there. So this is what's doing most of the work. This is what is absorbing the light, and what's transporting holes and electrons into the respective layers. So light comes in, photo excites an electron and a hole. They get separated via an external field, a voltage, a bias that we're applying on the device through these two contacts, this one here and this one here. And through that bias, electrons and holes go in opposite directions and get collected. Okay, so that's the device. Now, perovskites are this type of material that are very versatile. And so, like now going a little bit back into the actual material, they have this ABX3 structure, and they're actually the most abundant mineral on Earth. And they were first discovered as calcium titanate in the Ural Mountains. And they're just very abundant as this oxide. But they're also very versatile. So we can exchange some of these elements for other elements. So in the case of oxygen, we can exchange it for halide, iodine, bromine, or chlorine. In the case of this cation, calcium, which normally has a charged state that sits right in the middle there. For that, we can actually have an organic material, or we can have an inorganic, but it has to be normally a 1+ state. And then the metal here in the middle can also be swapped by many other alternatives. So the general types of materials that we're interested in are halide perovskites, and in which case we have the A side, which is that guy sitting here in the middle, which can be an organic layer, so that's methylammonium, carbon, and a nitrogen, or formamidinium, where we have 1 carbon, 2 nitrogens with the resonant bonds there. Or we can have the inorganic version of those, like cesium, has to be a charged state, 1+, 1+, and or rubidium. For the B side, so that's basically that guy kind of sitting here in the middle of this octahedron, that's the corner sharing with other octahedron. That we can have lead, tin, or germanium. That dictates a little bit of the band gaps of our material. And for the X side, so for those corner sharing group sites there, we can have iodine, bromine, or chlorine. Okay, so what happens when we go from chlorine to iodine and we kind of explore combinatorial structures of materials? We go from a material that absorbs in the UV, so we can make UV absorbing solar cells if we want it, or we can make a UV detector, for example, to bromine base, which are going to be more yellow, red. So if we were thinking about building integrated photovoltaics, for example, and we're interested in color, we can start looking at, for example, bromine-based perovskites. And in the near infrared, we have the iodine-based perovskites. Those iodine-based perovskites are going to be darker, although semi-transparent as well. Most of the work that has been done in the past few years has been this regime, because the darker the material, the more photons we're going to be absorbing, the higher the efficiency of a solar cell. That's where most of the work has been done. So questions so far? I want to also encourage people to stop me if I'm going too fast or if something is not clear. Yeah.
So the perovskites were found first. So do we mine them or do we make them?
We make them. So we can also mine them, but they're going to be the oxide type, which we don't care about.
Oh.
Except if you're in the ferroelectric field. The ferroelectric people love their perovskite, their oxide perovskites. But for us, we've kind of engineered them in the lab to have the halide part. We cannot find the halide of perovskites in nature. But we've used the oxide perovskite as a model material, it's a model structure to kind of plug in whatever elements and then do screening and say, okay, these ones are good for this one are good for that. So yeah, it's just a really good platform. All right, I'll move on. So one thing that we discovered very early on with perovskites, or maybe not very early on, maybe about 5 years ago. So 5 years into this discovery of perovskites and us making them in the labs and getting 20% efficiencies. We're making them, and no matter what we did, we pretty much got really high efficiencies. If you talk to somebody who has been in the semiconductor industry and tell them that we've been spin coating a liquid and making a crystalline structure and getting 20% efficiencies, they'll be like, you're crazy, right? Because silicon solar cell people might know this better than anybody. You need to have like 9 nines of purity in your material in order to avoid recombination dynamics that happen in the material. So, so point defects are very important in any semiconductor material that you're trying to develop. And this can be vacancies, this can be interstitials, and so on and so forth. Substitutional impurities is a big one, especially in industry. You don't want to have an iron contamination in your silicon ingot line because that iron implants itself and creates deep traps in the middle of the gap, and that creates a lot of trouble for your solar cell. And so that's basically what I'm trying to say with this graph here, is that most semiconductors are defect intolerant. So basically, you put any kind of defect and you create trap states that are in the middle of the gap. And so I'm trying to kind of show you here what that means. We have a valence band, a conduction band. We have a photon that comes and photo excites an electron into the conduction band. And that electron, if we put an electric field, we want that electron to, without losing its energy, without going down in energy here, basically extract it, bring it out of that conduction band as soon as possible. But if you have a trap state that is in the middle of your band gap, what happens is that that electron has now an incentive to go here, because it's easier to go into this state than go across 100 nanometers of material. So this deep trap state, what it does is it collects an electron. That electron sits there. Let's say it's 300 millielectron volts. That's really a lot of energy. It's an order of magnitude higher than thermal energy. So that electron wants to stay there and will not go up into the conduction band through thermal activity, through thermal energy. Instead, what it will do is sit there for a while and then finally go back down and recombine with the hole that left in the first place. So basically, this becomes a dead end, right? So that electron doesn't get out of the cell, and we don't register, we don't get current. In perovskite solar cells, what we have found over the years is that the defects that are formed from the impurities from processing these materials very cheaply, very rudimentarily, form shallow traps. So traps that are very, very close to the conduction band. And what that means is that state is so close to the conduction band that with just thermal energy, with just 25 degrees Celsius of energy, which is about 25 millielectron volts of energy, it can go back into the conduction band. And this process is what we call trapping and detrapping. So it gets trapped, it gets detrapped, it gets trapped, it gets detrapped, but the electron is kind of available to move around. And so even with a lot of defects in our material, we're able to get really high quality semiconductors. And so what this means is that if we compare cadmium telluride, which is a traditional semiconductor for solar panel manufacturing, and this cadmium telluride material was made by collaborators who made really, really high quality cadmium telluride at really high temperatures and very impressive facilities. You can see that that's the lifetime of electrons. So basically, that tells us how long an electron can be in a material before recombining. And the lifetimes are within 1 microsecond. And perovskites, you can see that with a much more rudimentary setup, with a lot of impurities, we have these lifetimes that are even longer than what cadmium telluride will have. Silicon, with the amount of engineering that we've done to it, has microsecond range. Yes.
Go back to the other previous slide. Is there a fundamental reason that there are no deep states in perovskite?
Yes, it's because of the SMP hybrid SMP orbitals that are the way they're aligned. When you remove one of the elements, so iodine or lead, for example, instead of the bonding and antibonding that is formed is very wide, and it just ends up being very close. Actually, sometimes depending on the chemistries, it ends up being inside of the conduction band. So it's all about the bonding. The SMP bonding that happens specifically in lead halide base. Yeah. Okay, so now kind of summarizing this whole aspect. So there's definitely advantages for us to produce high quality semiconductors in high equipment cost types of scenarios. And that's kind of what we've been doing for the past many decades. But also there's advantages on having lower quality and lower equipment costs, lower capital expenditures for other types of technologies. And I think that one of the things that Professor Rohatgi and my group are trying to do is to see if we can marry these two with a little cost, adding a little cost from the perovskite production side. Can we increase the value that this solar panel is giving out? Right, so we're not adding a lot of costs to the already very costly infrastructure. We're trying to basically add a little bit of cost and have potentially a lot of gain from efficiency point of view. In terms of the deposition methods that we're interested in, we focus a lot on evaporation. My group does, but we also do some solution. The reason why we choose evaporation is because this is a scalable process. So this is something that cadmium telluride already does for the deposition of those materials, but we would do them at much lower temperatures, right? Cadmium telluride, the positions are very high temperatures. We're talking here about sub 200 degrees Celsius evaporation. So very low temperature processing. So I have a couple of projects that are ongoing with industry. The first one with First Solar, where we're trying to develop different electron transport layers, because the perovskite is something that we kind of already know a lot about, and that's something that my group does on a regular basis. We deposit the perovskite itself by thermal evaporation, and I'm not going to talk too much about that today. But there's other layers that we need to make sure that they're deposited by thermal evaporation. And there's really very little on that. And we also need to ensure that they're evaporated by at low temperatures. So we're working here with chemists at Georgia Tech, the group of John Reynolds, who are developing some of the electron transport layers, molecular-based electron transport layers that we can evaporate and have different functionality that we want, that we care about. So these two layers are being developed currently under this project. Specifically, the evaporated ETLs, the perovskite is under another project, but both of these things are being developed here in my group to see how we can scale up some of the evaporation processes to industry. The other project that I'm working on is with Novelis, and this is for flexible perovskite solar cells. And a lot of this stuff is kind of under NDA, so I cannot tell many details. But what I can tell you is that there's a lot of incentive for us to try to develop materials that can be easily deposited on an assembly process in a roll to roll process, right? And so if you can imagine that we have this aluminum roll that is coming through the assembly through the manufacturing facility at Novelis, and we just start adding some additional layers that can give value to that material. We can think about incorporating things on buildings and other things. So we are working to try to understand how we can incorporate some of these materials into other types of surfaces that are flexible, right? So with aluminum, you can imagine we make a solar cell here towards the end of that process, and then what we do is we roll that piece of aluminum that has been encapsulated and finished, and we can ship it off. And the advantage of that is that really the cost of transporting glass is so high that this will be a game changer just in the transportation cost savings that we're going to have. Here are some pictures of materials that we make with different colors in our lab. You can see also semi-transparent materials. You can see here how we tune the band gaps. So here from very yellow, so 2.4, 2.5 electron volts, all the way to 1.4, 1.5 electron volt absorption. So we have a lot of tunability. We have a lot of high throughput. So I'll tell you in a couple of minutes about that. And here are some devices that we've made for that project where we have a substrate, we grow some perovskites on them, and then we actually make a device So here, each little pixel there you see, that's gonna be a device. And here's some morphological features of the perovskite that we have there. Okay, so just for about 10 minutes, I want to tell you a little bit about material science, because I told you a lot about the industry outlook, but I want to tell you a little bit about what my group does and what we're good at in the next 10 minutes or so. And we are very interested in crystal surfaces, what is at the surface in terms of chemistry, in terms of structures. We're also interested in terms of in the grain boundaries, so the effects of grain boundaries on optoelectronic properties of materials. And then finally on precipitates. So when you have accumulation of ions or elements in one specific spot. So let me tell you about what we're doing in terms of precipitates in my group and how we can characterize them. So that's the one wing of my group here, which is focusing much more on synchrotron-based characterization. So using X-rays to do mapping and other microscopy techniques. And the first technique that I want to introduce is called XBIC and XRF. XBIC stands for X-ray beam induced current. And the other one is XRF, which is X-ray fluorescence. And in combination, these two techniques, what allow us to do is look at them at the current extracted by a device versus the chemical composition. And I'll tell you a couple of examples. So how we do this, we basically have an X-ray source that is very broad, and we have a bunch of optical settings that allow us to focus that beam into 150 nanometer beam spot size. We can go all the way down to a couple of nanometers. So if we really wanted to look at atomic scale composition, we can do that, but that takes a couple of days to set up. So we normally do the high throughput measurement, which is 150 nanometer spot size. Okay, so here is a device that we actually bring to the synchrotron. And you can see that little gold strip that's the device. And here are the contacts. And then we can connect those contacts to an external source and measure the current that is being induced by those X-rays. So in the first part, the XRF part, that's the chemical part, we can look at, for example, that little corner there that is going to be gold. So you can see that corner, that patch of gold that looks very straight and nice. Actually, it's not so straight at the nanoscale range or the microscale range. But that's the gold signal, right? So that's that little corner there. And in principle, if we're applying a voltage, we should extract a current. And so if we're extracting a current, we should be able to see it from X-rays that are being shined. So basically the X-ray, very high energy, comes in, excites an electron, kind of similar to what I showed before. And that electron is being blasted basically almost out of vacuum, out of the material, but it's not. And then it stays there, thermalizes until it gets to the conduction band and it gets collected. So what we are seeing here is basically X-rays being transformed into current, which then gives a map that looks like this. So that's the XBIC signal, which basically tells us, okay, wherever there's a gold pattern, wherever there's current that's being passed, we can also detect on a spot by spot basis. This allows us to look at chemical maps like this. So here we have bromine poor regions, for example, versus a homogeneous film. So that's the chemistry. But if we want to do compositional analysis of how that is affecting current, we can see here, for example, how rubidium clusters affect the current of our device. So this is low current that is being tied to those rubidium heavy atoms. So areas where we have a lot of rubidium have lower current, and this allows us to say, okay, rubidium is a bad element to have in our solar system. So we're basically doing this correlative studies on what elements are good, what elements are bad for a solar cell. Okay, moving on to surface defects. That's something that we do also at a synchrotron. So we are interested in looking at surface chemistries, which actually we do here with XPS at Georgia Tech. But we do also X-ray scattering at very, very, very low angles. And what that allows us to do is look at surface defects in structure. So we do that at the National Synchrotron Light Source at Brookhaven National Labs, and where we can have this very powerful X-ray that has a specific angle, And when we have that X-ray hitting our sample, there's some scattering. And that scattering gives us a signal, and that signal tells us what structures we have in our device. And this is called GWAX. And so the lower the angle here, the more surface sensitive we are. And so here is a graph of that. So here is the angle. So really, really low angles, 0.01 degree all the way to 1. At 1 degree, we look at the bulk, and at 0.1, we look at the surface, or below, we look at the surface. So that's a penetration depth of about 2 nanometers versus 200 nanometers. So two orders of magnitude of difference in terms of the depth profiling that we can do. That gives us information like this, where we can basically differentiate between the bulk and the surface, and what kind of structures we have in there. For example, how materials degrade over time. We expose them to different environments. So here, for example, we expose them to heat and try to see, are those features surviving? And we see that they're not. So how stable are those features? How stable are those chemistries? And then, for example, after 40 minutes, looking at those features completely disappearing. So this allows us to probe the intrinsic stability of the materials before we even put it in a solar cell, because we want to make sure that the material itself is stable before we actually test it in a solar cell. So we do a lot of those studies at the synchrotron.
What are those 2D features?
This one's here.
Yes, sir.
Yeah, so these features here, this is a very thin layer that we put as a kind of a recombination layer or a passivation layer. And that is common in silicon solar cells. It would be aluminum oxide. And for us, it's an organic material, and the organic materials, you can imagine, the organic is not as resistant to high temperatures as aluminum oxide. So these organics, we're trying to tailor them to have different functionalities, maybe to cross-link so that they don't move. But here, this was our first indication that this organic is moving, and so we want to make sure that we design the materials, those organic molecules, so that they don't move, so that they don't show a very high degree of crystallinity, and then over time kind of fades away, right? So yeah, those are organic materials. Okay, and so that actually is a nice segue to what we're doing in terms of designing processes, materials, and devices. So the first thing that I showed you was more about what we do in my group in terms of defects characterization, but we also design materials, and we're collaborating a lot with chemists who help us make new materials and devices. And what my group is focusing a lot on is on the development of these perovskites, inorganic perovskite by thermal evaporation, because as I mentioned, industry is interested in having a scalable process. And with this, we've basically been playing around and trying to understand how this material can form into a perovskite. So far, we've been having a lot of trouble growing perovskites. That purple shaded area there, and this one here, these are impurity phases that we don't want. What we want is this little guy here. That's the alpha phase of the perovskite, which actually is not forming. And there's nothing really that we've done that leads us to forming the actual perovskite. We've been actually forming this kind of impurity phases from evaporation. And so a lot of what we're doing is trying to understand how to form those phase pure materials and what kind of things we can do to enable it. And then the other thing is that we want homogeneous phases, right? So we don't want to have one phase in one side and another phase in another. So a lot of what my group is doing is trying to make phase pure, basically like this guy here, the emission only in one band, to have a good semiconductor. These here, you can see several emission peaks. Those are going to be detrimental to a device, because we have many different phases kind of forming around. The other thing that we're doing is developing some ways of depositing atom by atom these materials. So here is a very high risk project that I've been working on for the past 5 years since I arrived at Georgia Tech. And how can we make organic, inorganic, hybrid materials by atomic layer deposition? And so here's our first attempt to make the first step, which is the inorganic part, lead halide, and which we can actually grow cycle by cycle. These are 10 cycles, and these are 10 layers of lead iodide. So one cycle gives us one layer, which is pretty remarkable for ALD. Here's 100 cycles, which actually we got about 70 layers in there, which is more close to what we want. All right, so high throughput device fabrication is something else that we do, and I'll go over this pretty briefly, but we do a lot of compositional mixing to try to understand how properties change. And so you can immediately see here, different band gaps, yellow, red in the middle, and dark. And so band gaps are shifting, so that's good. That's a tunability that we want. And we can do this experimentally, basically from solution is easier than from vapor, but at least to screen is a very good way for us to kind of work on this and identify materials. So in this study, we did actually 49 compositions, and we measure all the structure and all the property features. And so here's GWAX, X-ray scattering that we did on all those films. We did 49 of those at different angles. So we had hundreds and hundreds of data points that took years. It took about a year for us to actually go through all that data. Here we have also SEM images of all those different films. So these are thin films. You can see how different morphologies are enabled by the different chemistries. But again, high throughput, kind of brute force high throughput, because this is something that we're doing kind of manually, right? So how can we leverage what GTMI is doing in terms of automation to kind of help us discover the new set of materials or the compositional chemistries that will enable a high efficiency device. Again, here, band gap, for example, so we measure the different band gaps. You can see from bromine, changing the bromine or changing the A site, we see different band gaps. So here's the band gap in the Y axis here, the Z axis. And then finally making devices, right? So we are able to make devices, measure the current, the voltage, the fill factor, and the power conversion efficiency. And here the red will be the highest efficiency. So, somebody is manually making these devices, not really optimizing every single step, but kind of running through the standard recipe and making a lot of devices in one go. So with this study, I think we made something like 1,500 individual devices that were published last year. Okay, so conclusions is I don't have all of them kind of in a list here, but I think what we have here is an opportunity for us at Georgia Tech, because we have Q-cells coming in and a lot of interest from government to catalyze research on photovoltaics, and also through GTMI to create partnerships on how we can make this into something that is a little bit more efficient, right? So right now, all the stuff that I've been doing and all the stuff that we've been doing has been kind of at the lab scale. How can we work with GTMI and in general with Georgia Tech community to kind of bring this to industry, more industry relevant partners? And so I think that's the first conclusion that I have is that really we have a lot of opportunity to interact with industry and to be a key partner with industry at Georgia Tech. And the second thing is that really I think that the future of energy is going to be photovoltaics, or it's going to be a big part of it. I think we all can agree on that. We've seen it. We see that it's now being a big part of energy deployment. And so what's going to be the next frontier, in my opinion, is going to be the tandem architectures where we have silicon perovskite solar cells, or even perovskite solar cell tandems, right? So we can think about that too. And industry is very interested in that. There's about 12 or 15, depending on how you count them, startups alone in the US that are working towards commercializing perovskite solar cells. So So there's a lot of interest, there's a lot of money being invested in these new technologies. So I think that there's a lot of potential for us at Rototech being part of that conversation. With that, let me thank my group very quickly. These are our labs. This is where we make our materials and fabricate our devices. And we have a state-of-the-art lab where we do our growth via thermal evaporation in the back over there. Also metallization, so we have metals that we deposit there. In the middle here, we do all of our solution-based processing. It's a box that's dedicated for solution, so it can handle solvents and complicated things. And then here where we do characterization, where we actually measure the solar cells, measure things before exposing them to air to understand degradation mechanisms. And of course, grad students who have been part of this and research scientists and postdoctoral researchers who have been helping me with all the research that I've shown you today. And of course, the sponsors who have been very kind to provide funding to those that we're doing. And with that, thank you very much for your attention, and I'll be happy to take any questions if there are any.
All right. Have any questions?
Yeah, so question, I come from industry, I am involved with materials that go into solar manufacturing. Can you talk about packaging? I'm aware Perovskite has issues with moisture sensitivity and temperature processing in the lamination process. Can you speak to that? Is there any research being done in this area?
Yeah, we actually didn't show any of our stability data, but what we're doing right now is similar to what the OLED industry has been doing. We deposit an aluminum oxide layer after we finish the device. We deposit an aluminum layer, and we've actually have data of 1,000 hours thermal cycling and humidity cycling with no losses in performance. As long as we prevent the moisture and oxygen from percolating through with, for example, aluminum oxide layer, those devices are pretty stable. So I think that's the biggest concern. That's what we call an extrinsic degradation factor, and that's something that was worrying us a lot at the beginning. But as we were more aware of the mechanisms that were driving that degradation, and it was oxygen and water, and we started finding solutions for it. We realized, okay, this is not the biggest problem. The biggest problem is actually the intrinsic degradation mechanism, which is when you're applying a bias on your device, you have a positive and a negative, and that drives ions from one place to another. That happens in pretty much any material, right? So even in an oxide that is a rock, you have that happen. In halide perovskite, the halide bond is weaker than an oxide, and so that halide likes to kind of migrate and move around. So that's something that we're trying to figure out now how we can prevent that, because that's basically degradation induced by an electric field, by a bias, which is basically a solar cell all the time, at least when there's light. So we're trying to understand those mechanisms to see how we can fix them. But from the environmental concerns, we're in pretty good shape, I would say, in the field.
So these will process just like a traditional solar cell, silicon solar cell. Lamination temperature is the same. Encapsulants that go around it can handle the same temps as silicon.
Pretty much. I mean, you guys can tell me more about the temperature ranges for encapsulation, but from what I hear is sub 200 degrees Celsius, and I think that's perovskites have no issues as long as you stay within that range.
Thank you.
And there's other things that we're trying to do which don't require even any because also that costs money. So, for example, can we deposit polymers by some kind of spray coating process that will prevent degradation? Other questions?
Any questions online? Actually, I had a question, a couple of questions actually. For the roll-to-roll process, we're using the aluminum. I was just curious, the conductors you mentioned before also were ITO, and does the transparency need to be there for the aluminum? How does that work?
Well, I think the transparency has to be there for any tandem device anything that is opaque as a substrate, you need a transparent on the other side because you need light to go through. So you have to always have one transparent conductor. And unfortunately, we haven't been able to do it. I mean, First Solar has been working on this for a long time because they also have glass. They grow their substrate, their materials on glass substrate. They have, I think, FTO or some other combination of FTO, ITO, and maybe some AZO. But basically, that's been kind of a point that we've been trying to fix and has gone nowhere. Really, ITO and FTO are the best conductors that are also.
So the aluminum is serving as a conductor, but
Yeah.
since it's not transparent, I mean,
Exactly.
it's not
It's
ideal.
opaque, yeah, so light will not go through it, but it's a conductor, so you can use it as a contact. But then you have to have the light come from the other side.
Right.
Mhm.
And then I guess with some of the high throughput things you were showing at the end with the high throughput device fabrication, and what was sort of the enabler there to, to produce
Oh.
that high throughput?
The enabler was this.
Your lab?
I designed my lab so that people could make things very quickly, in a kind of assembly line type of process. And you can see here, these are small antechambers, large antechambers, so that people can move things back and forth quite easily in the small antechamber. Larger things it will take longer with the large antechamber because of vacuum, but the idea was to minimize the amount of dead time between moving things. That's one thing. The other thing is that the device architecture. So gonna be a pain to go back to that, but the device architecture that I have is 1 inch by 1 inch device with 8 pixels. That gives us a lot of data to play with. So like if 1 pixel is dead, you have 7 that are working. If you have only 1 pixel in a 1 by 1 inch and that pixel is dead, then you lost that device. So that device architecture plus having a system that allows me to measure in parallel. So I have this kind of robotic thing that measures solar cells, can measure 100 solar cells in 5 minutes and spit out the data. And we have a machine learning code that basically has kind of figured out how to spit out a presentation with all the details of the system, of the experimental setup. So yeah, we've been trying to do a lot of automation as much as we can within our constraints to be able to enable this high throughput fabrication and synthesis. So for us, it's always the synchrotron data that is hard because we have a lot of data from that, and it's not straightforward to automate the processing of that data.
Yes, sir. But the standard grazing angle, grazing incidence X-ray diffraction is not good enough. You need the synchrotron.
Yeah, and the synchrotron also allows us to probe hundreds of samples within 1 hour.
Got it.
So yeah, it's day and night.
Given the current status of stability, like you showed that different options for halides, different options for cations, right? Like cesium or what have you. What is the current feeling that which of these elements give you more stability, or it's not very clear?
I think there is, and if we've been exploring this a lot, and it's gonna be right around here. A mixture of formamidinium, which is a very large cation with 2 nitrogens, and the cesium. This pure cesium and the pure formamidinium, you can already see that this is already degraded. This is white. The pure formamidinium is very unstable. The pure cesium, here you cannot see, but this one is clear. It's also white. This one becomes also white very quickly.
So iodine is the front runner for stability right now?
Yeah.
Okay.
Because what happens is if you start mixing with bromine, or if you do like mixtures, bromine and iodine, the bromine segregates and the iodine segregates. And then you have multiple peaks, kind of like what I was showing. So like you have several emission peaks, and that means that you have heterogeneity. So we want to keep it in the pure iodine regime. And that also gives you the most narrow bandgap.
And the FA is right now a better choice than yours?
Yes, yeah, because the MA is 1 carbon, 1 nitrogen.
Right.
It splits up at like 100 degrees. It kind of splits up, and then you destroy your structure. FA splits up at 200 and something. So the thermal stability of FA is much higher than of NA.
And anything being looked at for lead replacement, any
Yeah,
candidate?
tin, but
Tin is
tin
yeah.
oxidizes to tin 4+. So 4+, sorry. And that also changes the structure. So tin is like, it's super unstable. Like you remove it from the glove box and it immediately turns white.
Thanks.
All right, well, we're out of time, so I want to thank Juan-Pablo for a fascinating lecture. I thought this was fantastic. No time to get to that, like the manufacturing aspects.
Yeah.
Material science.
Thank you. Yeah, I think it's also like, how can we collaborate?
Yes, sir. So, just a quick instruction here. So, you guys can go to the website, research.gatech.edu/manufacturing and then /past lectures. If you go there, you can see previous recordings to the lecture. So, with your permission, this will be recorded and posted on that site in a few days. So we will be able to have access to that. We will have fall break next week, so no lecture. 2 weeks from now, we'll have Connor Oakfoot, who's a CEO of another ATDC company, come talk to us about reality capture technology. He's with Ethos Imaging. Very fascinating. It's like a reality twin. So more information about that in a couple weeks. Thank you, everyone.
All right, good job.
Thank you.
Enjoyed the lecture.